Greetings and welcome, ladies and gentlemen. We're taking a look at some Cramer's rule problems, solving systems using Cramer's rule. These are all 2x2s. This is from a Kuta worksheet called Solving Systems of Two Equations, W/Cramer's rule. W/, of course, means with. Without is W/O, of course. So here we go. Looking at problem 5. I've got a system. You can see the answer there is infinitely many solutions, but let's find out how we could have determined that. So the first thing I would do is let's find the determinant of matrix A. So that would be -1, -1, 3, 3. And so let's see the determinant. That would be -3 minus -3. And I end up getting 0. And when I have that occur, that tells me either, well, first of all, it tells me that there's no inverse for matrix A, so I can't solve it for a unique solution. But that doesn't confirm for me whether there's no solution or there are infinitely many solutions. So unfortunately, you'd have to do some further analysis on this. Notice if I take the top equation, and if I, say, multiplied this by, I don't know, 3, let's say if I was going for the elimination method, I would have -3x and -3y and -3. And then if I combine that with the second equation, which is 3x plus 3y equals 3, these all cancel out and get 0. These cancel out and get 0. 0 equals 0 is a true statement, so there are infinitely many solutions. However, this does not mean that every solution works or every pair of numbers works. There are infinitely many of them, but they are only the solutions that happen to lie on one of these lines. They happen to be the same line in this case, of course. But if I was to solve that for y, what would that be? That would have been -y would equal x minus 1, so y would equal -x. Ugh, that's an ugly minus sign. -x plus 1. So the set of solutions would be the set of all x, y, such that y is equal to -x plus 1. So any ordered pair that makes this equation true would work, is essentially what they're saying. So it's not just every combination of x and y. So yeah, so anytime you have a 0 for your plain old determinant of your coefficient matrix, it's either no solution or infinitely many solutions. Taking a look at number 7 here. Let's find the determinant of our coefficient matrix. -1, 4, -2, 5. So that would be -5 minus a -8. So that's +3, I believe. So that one's nice. Then we'll have the x numerator, which is the same determinant thing, except instead of my original x coefficients, I'm going to replace that column with -2, -4, my right-hand side or my constants, right? So when I calculate that, I'll have -10 minus a -16, so that looks like +6. And then the y numerator would be similar concept, except this time I'm going to replace the y's column with the right-hand side of the equation, -2, -4. And we would have +4 minus a +4 equals 0. Now, that's not actually a problem for us because zeros and numerators are okay. So that means x is equal to 6/3 or 2, and y is equal to 0/3, which is fine. That's just 0, right? So that means my ordered pair is 2, 0. Right? Bam. So, good stuff. All right, Internet friends. Hopefully that helped you out.